Hello, I am Dr. M.G. Vijay, Department of Physics, MGM College, Udupi. Let us consider the last part of Unit 3 for the fourth semester, basically the Anderson's bridge and the Desauty's bridge. Usually, from the examination point of view, this particular Anderson's bridge will be in general used for the measurement of inductance, but it can also be used for the measurement of the capacitance. In general, different components, namely the resistors, inductance coil, connected in this particular fashion constitutes or it represents what is known as an Anderson's bridge. So in general, we can say this is the modified form of the Wheatston's bridge that you have studied in your PUC. The simplest Wheatston's bridge consists of only 4 components, in particular the resistors P, Q, R and S. Whereas in this particular case, the Anderson's bridge, it is said to be modified because we have so many other components that is added to this. In general, the Anderson's bridge is said to be having 2 different parts. First, if we are making use of the capacitor and the resistor here, along with this particular inductance, as I said, that constitutes the Anderson's bridge. If in this particular place, namely the headphone H and this particular source, if we make use of a battery and a galvanometer, then that is called the DC part. And in that particular case, we have to vary this particular resistor S for the zero deflection. The basic principle of Wheatston's bridge that you have studied in your PUC remains the same. That means certain amount of current enters this particular junction A. It divides itself into 3 different branches, namely I1, I2 and I3. At a particular value of the ratio of the resistors, it so happens that the potential at F is equal to the potential at E. Therefore, no current flows through this particular galvanometer. In that particular condition, the bridge is said to be balanced. In the case of AC part of the Anderson's bridge, here we have the headphone and here we have the AC source. Now we are going to vary this particular resistance, small resistance R, such that no sound is heard in this particular headphone, namely H. As I said, the basic principle is going to be the same. No current flows in this particular part of the circuit FE when the potential at F is equal to the potential at E, and that particular condition is what is known as the balancing condition for the bridge. Whenever we make use of the AC circuits, we have to remember the inductive reactance of the inductor coil is given by the expression J omega L, and capacitive reactance by the expression XC is equal to 1 over J omega C, where J stands for the imaginary number, that's equal to square root of -1, and omega is the angular frequency. You have studied things in your PUC class. So in general, when the bridge is said to be balanced, we have to make use of the Kirchhoff's current law and the Kirchhoff's voltage law. According to the Kirchhoff's current law, whenever the current enters one particular junction, the sum of the current that enters the junction should be equal to the sum of the currents that is leaving the junction. Since the bridge is balanced, at particular point, namely F, there is no flow of current from F to E because F and E are said to be at the same potential. Therefore, the current that enters this particular point F will move towards B, the same current I2. So here current I1 is entering the junction B, I2 is entering the junction B. Therefore, the current that flows through this particular part of the circuit BD will be equal to I1 plus I2. Similarly, the current I3 is flowing in this particular arm AE because of the fact that E and F are present at the same potential. The same current I3 flows in this particular branch, namely ED, so that the current that leaves this particular junction D is equal to I1 plus I2 plus I3. Now, we have to make use of the Kirchhoff's voltage law, according to which the algebraic sum of the current and the resistance or the impedance should be equal to the algebraic sum of the EMFs of the voltage sources. Again, you have studied that particular thing in detail, and that is applicable in the case of a closed loop. Now let us consider the Kirchhoff's voltage law to the closed loop A to B to D to E to A. That means we have to start from point A, we have to move in this particular direction A to B, and then B to D, and then D to E, and then E to A. In some of the textbooks, they write it in the clockwise direction or in the anti-clockwise direction. For the sake of simplicity, I have considered that particular thing to be a straight line, but the direction of traverse is in the clockwise direction. Now let us see what is going to happen to the product of current and the resistance. Here the direction of traverse is A to B and the direction of flow of current is I1. Therefore, current is taken as I1 only, that multiplied by the resistance, namely P. Then we have to move from B to D. The current is I1 plus I2. It is same as that of the direction of traverse. So this is also plus, and this is Q. So I1 plus I2 into Q. Next, we are moving from the point D to E, whereas the current is moving in the opposite direction. Therefore, current I3 is to be taken with the negative sign. And the same thing is true with reference to the branch, namely E to A. Therefore, we write it as minus I3 into R plus J omega L plus S. And in this particular closed loop, there is no voltage source. Therefore, on the right hand side, we have 0. Similarly, let us consider the Kirchhoff's voltage law for the closed loop A, B, F, A, B, F, A. So here again, it is the product of current and the resistance. I1 is in the same direction of that of the traverse. So this is I1P, and the current here is flowing in the opposite direction to that of the traverse. So it is minus I2. Again the same thing here. So it is minus I2. So we get I1 into P is equal to I2 into small r plus 1 over j omega c. Similarly, we can consider another loop, namely AFEA, A to F to E to A. In this case, current I2 is positive. Here there is no current. And in this particular branch E to A, the current I3 is minus. And no source of voltage. Therefore, we have I3 is equal to I2 divided by j omega CR. These are the three important equations that we have written. So substituting equation 2 and 3 in equation 1, we get this particular equation. And here we can see the common factor, the term I2, I2, I2 and I2, which is common. Therefore, we can remove that. And then we can slightly rearrange the terms after opening the brackets. And then we can write the terms as sum of the real number and the imaginary number. The same thing we can do it here. So r small r q by p into small r plus q is the real part of the left hand side, and the third term is the imaginary part. Similarly, on this side we have L by CR as the real part and this as the imaginary part. And we can equate the imaginary parts on the left hand side with the imaginary part on the right hand side. And then we get 1 over j omega c, 1 over j omega c, which is common on both sides. Therefore, we are going to get the relation P by Q is equivalent to R by S, which is same thing as the condition for balance in the case of Wheatstein's network. Now let us consider the real parts of the equation 4 from left and the right. So if you rearrange the terms, we get L is equal to C into capital R Q plus small r into capital R plus R Q by P. But we know P by Q is equivalent to R by S. So we can write this particular equation as L is equal to C into RQ plus small r into R plus L. And therefore the inductance of the coil can be determined. If we know the numerical value of L, then this particular equation can also be used for the measurement of C, and this is one of the experiment which is there in the next semester for the final year BSc. Now this is anyway again the method for measurement of the capacitance. This is again in the modified form of the Wheatstone's bridge. Here we have two resistors on one side and two capacitors on the other side. Because we are going to connect AC source, here we are having the headphone. Now let us say R1, R2, C1, C2 are connected as shown in the figure. And let us say our aim is to determine the unknown capacitor C2 provided R2 and C1 are known. So R1 we are going to vary, and then R1 is varied so that no sound is heard in this particular headphone. Then we can make use of the condition for balance. In general, we can say the impedance of the ratio of the two sides is equal to the impedances of or the reactances of the corresponding sides. So Z of AB divided by Z of AD is going to give us Z of BC divided by Z of CD. But we know what is Z of AB, it is pure resistor, so it is simply R1 by R2. And Z of CB by Z of CD, it is 1 over j omega C1 whole thing divided by 1 over j omega C2. That is going to give us C2 by C1. Therefore, we can write the expression for C2 as R1 by R2 into C1. If we know the numerical value of C1 and R2, R1 is determined by making use of the experiment. And therefore, the numerical value of this particular capacitor C2